Hi, Charlie. Sorry, you're on mute. I can't hear you. You have your speaker on mute.
Yes. How are you? Sir? Can you hear me?
I'm saying you have your speaker on mute. Can you hear me?
Yeah, I can hear you.
Okay. It could be that I have my microphone on mute.
Well, I can hear you fine.
Okay, I can hear you now.
Yeah.
Okay. So
Maybe I'm looking away.
I'm going to give us another, say, 2 minutes, and let's see if anybody else hops on.
Okay.
Yeah. All right.
How many people are in the class?
We have 16 students. So
Okay.
yeah. Surprisingly, last time it was just 2 people on the last Zoom session, and let's wait and see what we're going to have today. But I'm going to make sure to record this so that they can go in and check, because I think there's certain things that might be confusing, especially in the latter parts of both chapters.
Right.
Okay.
When you record it, is there any way you can send it out as a podcast?
I'll save it to, because the problem we have usually is that if we upload it, say to Blackboard, it takes up space. So the university advises that we save it and maybe post it to YouTube, which is what I think I'll do, and then send out the link to YouTube.
Right.
Yeah. So that should be easy to access.
All right, because I spend a lot of time driving.
Okay.
And I listen all the time, and it's a great way for me to learn. I'm an auditory person anyway.
Yeah.
So hearing something over makes a difference.
Right. That's true. All right. Let's give him 1 more minute, and I'll just do something real quick.
Did you look at the any of the quizzes that were put in yesterday?
No, I haven't actually managed to have time to look into that, just because I was down with the flu for the past 2 days. So
I'm sorry to hear that.
Yeah, I'm almost back to 100% today.
Uh-huh.
Yeah, and I'll try and see if I can get through
There's
them.
a lot.
Yeah, how was the quiz?
There's a lot of. It was good. I'm still struggling with some of the part of it. So, like, one of the questions in the quiz, it put one part of data on the horizontal axis and one on the vertical, or opposite that. Okay. It would copy out of the spreadsheet. So I ended up just going in and swapping the columns. Then I did the thing, and then it put the right axis. But there's got to be a way that Excel could. There was a button that said switch axis, but it totally changed the graph, and it wasn't a scattergram anymore. So I was a little frustrated with that. I probably spent an hour and a half in front of me just to change the column.
Oh, okay. Oh, well,
for people that are good with Excel, this is BAP concepts easy. It's the Excel stuff that's a lot of my time.
Right. Yeah. Okay. Well, I'll check and review to see if there's you finally managed to get through it though.
Oh yeah, I think I did pretty good on it.
Okay.
There was a question, was it a direct or indirect it was in the last part.
Okay, let me pull that up.
I don't remember, but anyway, and I could not figure that out. I thought it was a direct correlation. It was so close to that 45-degree on the graph on the scattergram.
Okay.
The question was, did the bigger houses have a higher price? Was there a correlation?
Yes.
And I said, yeah, it was direct. If it was indirect, would mean that it'd be all over the place, right? The scattergram plots.
Indirect. Now, direct correlation is if you look at the points on your scatter diagram and they seem to have a pattern towards it. And in your case, you say you could actually put a trend line that would have shown like a 45-degree. That would be a direct relationship.
That would be direct, right?
Yes, and that it could either be
that's what it
direct, positive, or direct negative, which would have your line sloping downwards. Which would just be a negative relationship between the two different variables.
And that would make it indirect.
Yeah, I'll check to see once I start grading the quizzes. And I think it's 6:04, so let's go ahead and
Okay.
jump into what do we...
It said, is the relationship direct or indirect? And I said direct because it was a 45-degree angle.
Okay, yeah.
So, now I think I did okay on it.
Okay. All right, so I'll quickly walk us through chapter 5, and if there's any place where you might need me to talk a bit more about, just let me know. I'm going to share my screen with you. I have a PowerPoint that I'll quickly go over. Okay, so this is chapter 5. And chapter 5 basically walks us through introduction to probability and what we should know from a business perspective when it comes to probability. And there's quite a bit to cover in chapter 5, especially given that you had 2 chapters to cover this week. But basically, if you look at the basics, what's probability? From the most basic perspective, you're looking at a situation where there exists a measure of uncertainty. Okay, you don't know the outcome with 100% certainty. All right. So in your book, you have all this information with the chart that I'm showing here, where you're shown the probability associated with different things. For example, what's the chance that it might rain in Florida this year? And in this case here, we have a 1, meaning that there's going to be almost certain that we're going to have rain in Florida. So this part should have been pretty easy for you to follow through in the book. It talks about experiments as being a part of the whole probability process. Because we have that uncertainty, we use experiments to try and gain a measure of certainty by repetitively trying to find what the outcomes would be if we tried to do a test a number of times. Okay, so for classical probability, which is the most basic approach to probability, you're just basically looking at something as simple as how many positive outcomes are you going to have from a whole bunch of different outcomes. Okay, did you have any questions on this part of probability? Should be pretty straightforward up till this point. And then we had a breakdown of the different types of probability to either objective versus subjective. The only difference is that subjective is usually based on the person who's actually doing the experiment, collecting information, and sometimes injecting their own personal perspectives into that whole probabilistic approach. When it comes to the rules of probability, how to add them, how to multiply them, we have 2 types of, the 2 main rules. There's the special rules and the general rules associated with both addition and multiplication. And the thing that I would like you to remember here is that if you have an addition, or if you, okay, so we have, welcome, Devin. Yeah. So I'm just brushing through the rules of probability here. So when you come across a probability question and you're not certain on what formula to use, I always ask that you ask yourself what word is used in between the 2 different things. Like, is that or an and? Okay. If you have a problem that has the word or, you're looking at an addition. If you're looking at the word and, you're looking at a multiplication. Okay, so that's something that you might have to try and remember. Or equals to an addition, and equals to a multiplication. Okay, so like in this case here, using the special rule of addition, we're looking at a situation where you can have 2 outcomes which could be, in this case, event A, event B. And you asked, what's the probability of either event A or event B? Okay, so in this case here, these are 2 events which don't overlap. Okay, that's an or situation. for me to calculate the probability in my mind, that automatically should ring that that's going to be an addition. Okay. So in this case here, I would look and ask myself, what's the probability of event A happening? And I'll add that to the event probability of event B happening, and that'll give me the solution to that probability. Okay. So in the textbook, you'd have this example that excuse that. And I'm going to have a whole bunch of pop-ups here. But in this case, we have an example here of a machine that fills plastic bags with a mixture of beans, broccoli, and other vegetables. Most of the bags contain the correct weight, but because of the variation in the size of beans and other vegetables, a package might be underweight or overweight. Okay, so in this case here, the experiment was that they took 4,000 packages and tested their weights. And the question here is, what's the probability that a particular package will either be underweight or overweight? So those are the two things that we want to look at. What's the probability of underweight? What's the probability of overweight? And it's as simple as just a simple addition. This should be pretty simple, pretty easy to go to resolve. Again, the thing to remember is it an or question or is it an and question? Okay. So the complement rule is another approach to pretty much the same thing. If we want to try and find an answer to a question, sometimes it might be easier to just look at what's the probability of some certain thing not happening, and that then becomes your answer to the complement question that you might have. Okay, and that's I believe the question that I put in the homework assignment. I'm not too sure about that, but that again shouldn't be too hard. Now, the second part to the addition process is what we call the general rule of addition. And this occurs in situations where we don't have two events that are mutually exclusive, okay? The fact that event A happened does not mean that B might not have also happened at the same time. So there's some measure of, that whole concept of independence is no longer a consideration here, okay? Again, this is an or question. The only difference is that because we have some overlap between event A and event B, we have to ask ourselves, we have to take into account this overlap and make sure that we're not double counting this overlap. Okay, so if you look at the formula that we have here, the probability of A or B, we first of all get the probability of A separately, the probability of B separately, and we subtract from that the joint probability of A and B, okay? Because that would be that region of overlap here, which if we don't take into consideration, then our probability won't be accurate, okay? So if you look at the formula, let me use a pen, so here. This second part right here. I don't know why my pen today is green. This basically takes care of this overlap such that when you're doing that addition of the two events, you're not double counting region A plus B, okay? So that then is one other thing that we can do when we're looking at probability. Let me escape, oops. Let me close this out. I don't think we would need, actually, let's go over this real quick. And this should be easy to follow. It's something that you might have seen in your textbook. So we have 200 tourists in Florida. We're told that 120 go to Disney, 100 go to Bush. And we want to find what's the probability that tourists went to either Disney or to Bush, okay? And in this case, we're not looking for that joint probability. We're just looking for the probability of how many people, what's a total probability of people going to Disney or Bush, okay? And As you can see, the process is pretty straightforward. You get the probability of Disney. In this case, we're giving it 60% or 0.6. Add to that the probability of those going to Bush, which was 50% of the tourists. And from that, you can subtract that joint probability of Disney and Bush. Okay, so the last probability we have here is an AND, which we've not discussed prior, but if you remember what I said, we talked about AND. Whenever you see the AND, that's a multiplication. Okay, so if you're trying to determine what's that probability, it's a simple multiplication where you're going to pretty much look at what's the probability of Disney, probability of Bush, multiply those together, and you'd come up with a certain number. Okay, so I'd like us, if I'm going too fast, let me know, but there are certain parts of the chapters which might be slightly more involving, and that's where I'd like to go to. Okay. So we already talked about the special rule of multiplication. This is where we have your AND, probability of event A and event B happening. That would be a multiplication. And now, this general rule of multiplication is slightly more complex, okay, because it involves what's called a conditional probability, okay? And a conditional probability is basically a probability that can only be calculated after you've calculated another probability, okay? So in this case here, if you have if you're trying to do a calculation of, let's look at an example. It might be easier to explain that way. Okay, so look at this situation where we have a golfer who has 12 shirts total. Okay, 9 of the shirts are white, 3 of the shirts are blue. And we're told he wakes up in the dark, so he grabs a shirt, he doesn't see what color the shirt is, and he does the same thing the very next day. So there are 2 consecutive days when he wakes up in the dark, puts on a shirt, and there's a probability associated with what color that shirt is going to be. Okay, so the question that we're given here is, what's the probability that both the shirts are white? Okay, so if we had to consider this and write it down statistically, we're looking at a situation where I'm asking myself, what's the probability that the shirt that I pick on day 1 is white, and the probability that the shirt that I pick on day 2 is white, subject to the fact that I picked a white shirt on the first day. Okay, so this is a conditional probability because we are trying to figure out what's the probability that both the shirts are going to be white. Okay, so the second pick that he's going to have is conditional on the fact that the first pick is going to be white. And so this is what we see here. The probability of W1 would be what? 9 divided by 12, right? So we have, we actually have it already here. So 9 divided by 12 is a probability that on the first day he picks up a white shirt. Okay. We're told in the question that he does not return the shirts to the closet. Oh my goodness, it's the worst line I've ever drawn. So this is part of what you must factor into your formulation. So he does not return the shirts into the closet. So it means that the very next day he doesn't have 12 shirts, he now has 11 shirts. Okay, so on the second day we're asking ourselves, what's the probability that he's going to pick a white shirt? Okay, he has 11 shirts, and we assume that on the first day he picked up a white shirt. Okay, so if that's the case, then we are down to 8 white shirts. Okay, so this is a conditional probability that his options on the second day are pegged on the options that he made on the first day. Okay, so in this case here, the probability of white shirt on the first day and a white shirt on the second day end up being the the multiplication of the 9 divided by 12 multiplied by the 8 divided by 11, and that gives you your conditional probability of 0.55. Okay. So this is in situations where you have a draw without returning back into the pool. Okay. So you have a conditional probability, and it might seem complex, but it really isn't that complex. All you have to remember is that if you are drawing from a pool of product of a pool of people, and you're not putting that product back in, it diminishes the amount of product available to you to source from. Okay, so that's and I believe I'd put a question in the homework assignment, something similar to that. I think it had to do with houses in the neighborhood or something. I'll have to go back and check. All right, so all right, contingency tables. I think this is something that should be pretty straightforward. I'm not going to go too much into it. But this tree diagram is something that I think you should take time to review. The tree diagram is just basically another way of looking at the conditional probability. Okay, a conditional probability, again, is you making a subsequent selection on the basis of something that was done prior. Okay, so in this case here, let's go back over this case. I guess we might have to discuss this further. So we have a situation here where we're looking at the number of movies watched in a month from 0 to 6 or more. And we're also looking at age. Okay, so we have people who are less than 30 years old, people between 30 and 60 years, and then 60 and older. Okay, and if we're trying to figure out the number of movies watched by these different age groups, we first start off by looking at the age, okay? And we're told that there are people in different age groups. There are people, a total of 100 people who are less than 30 years of age, 225 who are in the second category, and finally 175 in the final category. So the number of movies chosen by people in this category comes after you've, the initial decision was to break up this group of people by age, okay? And the reason why we might want to do this is try and figure out, is there any difference in movie watching patterns between those in the 30 or younger age group or those in the other categories? And so this tree diagram just basically breaks down what we have here in the contingency table and makes it easier for us to visualize what the contingency table actually looks like. Okay, I don't think I'll ever ask you to draw a tree diagram, but it's good to understand what exactly you're looking at when you look at the tree diagram. Okay. All right, this is another interesting part. Do you guys have questions before I jump here?
You one slide.
Go back.
Just back up that one slide. You say this part here that you have up right now, you're saying we won't have to do that or will have to do that?
No, we'll not.
Okay.
It's good to know about it, but to be honest, in my 15 or so years working in corporate, I never had to ever deal with tree diagrams, and I don't know anyone in any other department who ever did tree diagrams, so I don't think it's worth your time. It's good to know it exists, but for the purposes of this business class, I think it's just good information.
Works for me.
Okay. And this statistics is actually a lot of things that we do that might hardly ever apply to any of you, but there's nothing as beautiful as one day coming across a situation where you actually get to apply something that you did in a statistics class, and you're like, huh, okay, I learned this some 20 years ago. All right, so Bayes' theorem, okay, is a theorem that's used when you have information, possibly historical information, and you come across some new information that could possibly shed some more light on a specific situation that's been a phenomenon that's been there in the past. Okay, and an example I could use is, let's look at the US electoral system and say I know from historical information that 5% of the US electorate are independents. Okay, I really don't know what the population is, but say 5% are independents. Okay, but I decide to go out and do an experiment and test, is that really accurate? I go out into the population, take a data sample, and with this new information, I want to see how accurate my findings are compared to what that prior information was. Okay, that's a situation where I might want to take into use a Bayesian approach. Okay, so Bayes' theorem basically relies on two pieces of information. There's prior information and then there's posterior information. So prior information that's already available. The posterior information comes after you've gotten new data from some source somewhere. Okay, usually through experimentation. And it gives you a more realistic, more revised version of what the probability should actually be. Okay, the formula looks complex, but it's really not that complex. It kind of like piggybacks off of what we talked about when talking of conditional probabilities. Okay, so rather than looking at a formula, let's look at an actual situation, an example that might shed more light. Let me clear all drawings. Okay, so suppose 5% of the population of a country have a disease, and A1 represents a part of the population that actually has the disease, and A2 represents those who do not. Okay. So we know that A1 are those people who are sick. So that's our 5%. That's mentioned right here. So if 5% of the population A1, A2 then becomes 95%. Okay, that's information that I guess they got from historical research that had been done. Okay. Now let B denote a test result that shows the disease is present. So somebody went out there and took tests of people to try and show that the disease is present. Okay. So now we have some pieces of information here. The first initial pieces of information that we have, what we call our prior information, are right here. Okay, I'm going to just write this. This is prior information available to us from historical sources. Let me use my finger. I can write on my screen. Oh my goodness. All right. Just assume that that's an O. So that's our prior information. Okay. Now the second part of what we have here, this is new information that comes after somebody's gone out, collected some new information. Okay. And so the new information was, this person is testing to see that the person has the disease or not. Okay. Now, look at this conditional probability A. Okay. So B is a test, and the test has two options. The first part of the test is either the individual has a disease, and it's actually true that the individual has a disease, because the test could be wrong. Okay, if you go back to look at a pregnancy test, maybe you should have used a pregnancy. That might have made might have been easier to understand. Let's use a pregnancy test. Let's assume this is a no. I don't know that people are going to crucify me for that, but let's assume that this is you take a test, and the test comes back positive. This person has a disease, and in actual fact, the person does have the disease. Okay. If that's the case, then the probability of this this conditional probability, the B, being that the test is true and this person actually has the disease, is 90%. Okay. The second alternative would be that the test shows that the person has the disease, but the person actually in reality does not have the disease. Okay, that's a second alternative that's available to you. That could happen. Okay, so with this new information, we can now go out on the street and run a test and see whether or not somebody is able to actually be tested and fall within the range of information that we're given here. Okay. So say, for example, I want to test if somebody has this disease. Okay. I get somebody off the street, and with the information we have here, we can now use Bayes' theorem to try and determine how correct the test is going to be. Okay. So if we look at the formula that we have for our, let me start with the upper portion of this here. Hopefully, if you look at this first part here, it looks like what we did for the conditional probability testing. Okay. So basically, Bayes calculates what's the probability A, or what's the prior probability multiplied by that posterior probability. Okay, and you divide that by the same thing added to the should I call it the alternate? Okay, so basically you're going to add this part C to part D, and the sum of that becomes our denominator, and we use that to try and find the probability of the test that we took. How accurate would the test on average be? Okay. And in this case here, we come up with a number of 0.24. Okay. And what does that tell us about this test if your probability is 0.24?
I'd say it's not only 24%.
It's not what?
Not too accurate if it's only 24%.
Yes, that tells you that this test is not too accurate, and you might not want to use it for reporting results. You might want to find a different approach to your testing to be able to test whether this is actually accurate. Okay. So that's Bayes' theory. It basically looks at, again, if you have information and you want to test that information with some new information, and try and see if you can come up with a measure of accuracy of information that exists based on this new information that you have. Do we have another example here that might shed slightly more light? No. Okay. Anyway, and again, feel free to hop in anytime you have a question. Okay, the final part of chapter 5 just basically takes us through multiplication rules. Okay, and ways to combine different variables together. Okay, the most basic approach would be when you just use a multiplication formula, and that's basically in a situation such as the example we have given in the book. You have an auto dealer who has is selling cars for around $30,000, and you have three different options: either a convertible, a two-door, or a four-door. And then you have two options for your wheels. Okay, either wire wheel covers or solid wheel covers. Okay, and the question here is, how many different vehicles can the dealer offer? So this is the most basic. This is the simplest counting or multiplication problem you would have in our book. It should be pretty straightforward. I won't waste too much time with it. But you also have questions associated with what are called permutations and combinations. And those are of interest to us. Okay. because these enable us to find different ways to, if you're looking at, for example, scheduling workers, or how many different ways can you group different things together, you might want to consider either permutation or a combination, okay? A permutation would be used in situations where the ordering of the different groupings that you can come with is important, okay? A combination doesn't really care about ordering or grouping. It can just put together different groups of items or variables together and just do a calculation of how many different alternatives you can have. Now my battery is running low. That's not good. I believe I have 13%. Okay. Now I have a question for you both. Did you guys have any questions on this? Before I take a quick break, let me explain permutation.
I didn't have any.
Okay. So permutations, that's why we have all this nice stuff with the exclamation marks, okay? And if you look at the permutation formula, we have 3 letters here, an N, a P, and an R, okay? So basically, whenever you have a permutation problem, you're gonna be presented with a total number of variable, total numbers of a specific number of objects that are available to you. And you're told to select from these total number, a certain number, and find out how many ways you can mix and match those number of variables, okay, or objects, okay? So the formula here, n exponential divided by the difference between n and r exponential, provides you with that calculation. And basically what this does is, rather than have you try to list all the different combinations, it gives you a quick formula that enables you to do this without having to list down 101 different combinations. If you have a situation where you only have like 3 variables or 3 objects, it's really no big deal. You can actually do this by hand, like the example we have here. Here we're told that there are 3 electronic parts to be assembled, n equals 3, okay? And all 3 have to be inserted into the component. So you have to use all those 3, and you asked how many different ways can we insert these into the component, okay? So one way to do this would be to do what we have here, just list them all down and try and write down all the different combinations, which really doesn't take that long if you have only 3 letters, because you can do that in less than 30 seconds. But if your permutations here, if your n, for example, was 20 and your r was 5, then all of a sudden that's going to become something so ridiculously hard to try and, or it'll just be so time consuming, you won't be able to calculate that, okay? So in that situation, then we find it makes more sense to just quickly run a permutation calculation, okay? So if we did the very same thing, but instead used n equals 20, as I said, and let's have our r equal 5, okay? So basically we have 20 total objects, and we have to try and arrange them in groupings of 5. Okay. Now all of a sudden this becomes something that I'm just trying to think of how many lines of data I'll have to do before I get the full count. Excuse me. But let's see if we have that 20 exponential divide by 20, which is our n, minus 5.
What does the exclamation point mean?
So the exclamation point basically says you're going to multiply that number by the next lower number by the next lower number. So it'll be 20 times 19 times 18 times 17 all the way down to 0. Sorry, excuse me. My food is getting to me. I mean, all the way down to 1. Okay. So that exponential just basically says that whatever number you have as your n, multiplied by every other number lesser than it, all the way to 1. So the 20 exponential here is 20 times 19 times 18 times 17 all the way to times 1. Okay, and in the denominator here, that'll be the difference between n and r, which would be 15 exponential, which means it's 15 times 14 times 13 times 12 times 11 times 10 all the way to 1. Okay, I hope that makes sense. So
Well,
that is a lot of math.
Why that is, but it makes sense. I was going to ask you why that is, but that's all right. That's just probably, we don't go there.
Why? It's because you're trying to get all the different combinations for all the combinations that you could put these numbers together. Trying to find a better explanation. I don't really have a better explanation off the top of my head for why we calculate exponentials. But
that's all right. Just go ahead. As long as I understand the formula, we're good.
So if you come across such a question, I don't want you to be doing it by hand. Use Excel. It'll make your life much, much simpler. So let's open an Excel spreadsheet. Okay. Nope. Where is my Excel? One moment. Okay, so open.
Your Excel spreadsheet is not showing up on the video. It's almost like it's frozen up. I can't, you're not moving or talking. I can't hear you.
All right. Let's try this again.
Much better. I can hear you now.
Okay. Can you see my spreadsheet?
Yes, I can now. Before it was just very weird.
Okay. So so remember let me just use this pen. We had the permutation formula where we looked at n exponential, and
Right.
say that you subtract from that exponential, okay?
Mm-hmm.
And basically, anytime we have that n exponential, it's basically going to be that n minus 1 times that times, let me just write this down because it's going to be hard to describe. So say we have the example that I gave, that was our n was 20.
Right.
And the different ways that we wanted to combine that was 5, which is our r. And you
Right.
see that that's going to be 20 minus 5. And again, exponential. If I was to write this out, this will take quite a while, but it would be 20 times 19 times 18 times 17, and so on and so forth, times 1. All over n minus r was 20 minus 5, which is 15. So it'd be 15
times 14 times 13, right?
Yeah, and all the way, okay? But I don't want to do that. And even if I did that, it's pretty simple to calculate, because I'll basically just cancel out all that and divide that by, cancel out all the 15 times all that up there. And then just multiply 20 times 19 times 18 times 17 times 16, and I'll get my answer. Okay? But because this is a business class, we use Excel. We have, oops. The EXP function, okay? If we use EXP, it gives us that exponential function that multiplies all that in one calculation. So I would do exponential of 20, and it'll give me the results for that in one step. Okay, and I'll do the same for the denominator, which was exponential of 20 minus 5, which we know is 15. And I get that number. So then I divide these two numbers, divided by this denominator, and I get a number here. And this, hold on a second. Why am I having, I'll round this off to 148. Okay. So I would have around 148 different ways in which I can combine 20 objects 5 different ways. Okay. But there's something wrong with this exponential formula. Give me 1 second. Put my commas there. Nope. I want to check to see if we can use exponential distribution. No. Okay. Yeah. So that's one way you could do it in Excel, is to basically use the exponential function and use that to calculate what the results would be. So rather than in the example where we had 3 multiplied by 2 multiplied by 1, you'd instead try and use the exponential function and use that to calculate your answer. Okay. So that's a permutation. Sometimes we have a situation where we use what's called a combination. Okay. And combination, we're not really interested in the ordering of what we have. Okay. Just interested in how many different groups can we have, not necessarily in the order that we had here previously, where we're trying to see how many ordered groups of 3 could we get, okay? So the only difference between what we have for, the only difference between what we had and here is that now we also include an R exponential to the denominator, and then we recalculate what we have for to give us a combination. Okay, so the example given here is of a movie theater that uses teams of 3 employees. So we're going to have groupings of 3 to work the concession stand every evening. There are a total of 7 employees available to work. How many different teams can be scheduled in this specific scenario? Okay, so we have seven employees, and these 7 employees can be mixed up in any different, number of different ways. And if you use the combination formula, it gives you how many different ways you can juggle those 7 people around, and you come up with a total of 35 different groups of employees that can be scheduled. Okay. So that is that. Did you have any questions on the homework for chapter 5? No? I can't see your...
I thought I was unmuted. No, I didn't.
Oh, okay. All right, so let's move on. Let's quickly go over chapter 6. I'm trying to get this to... Okay, so let me pull up chapter 7. So we skipped chapter 6 and we'll do chapter 6 next week. We're going to start with chapter 7. It talks about continuous probability distributions. Okay, and basically probability distributions looks at if you have a bunch of data points, how do you describe how they are with regards to the mean, the median, how those data points related to the mean or the median. Okay, so there are very many different types of probability distributions out there. In chapter 7, we discuss 3 or 4 basic probability distributions and what are their characteristics like. Okay, so we start off with a uniform distribution, which is a most basic distribution. Okay, and the thing to remember with this distribution and every distribution is that the area...
Can I interrupt you just for a second?
Sure.
So we've got homework on chapter 6, but no homework on 7. Is that correct?
No, we have homework on chapter 5 and 7.
5 and 7. Okay.
Yeah, if you check we're not covering chapter 6 this week.
I see where it is.
Yeah.
Gotcha. Okay. Gotcha.
So for anytime you talk about uniform or a distribution in general, the area that a distribution, if you visualize it, the area of that graph that you have is a full range of probabilities or possibilities available to you. And the area itself should equals to 100% or to 1. Okay? Meaning that that probability will cover all possible potential outcomes that you can expect. Okay? Now, the uniform distribution is unique in that the probability at any given point in the distribution is pretty much the exact same. Okay, it doesn't change at all. It's always the same figure from beginning to end. Okay, and that might not make sense unless you quantify it with an example. So the example that's given in the book relates to wait times at a bus stop. Okay, and we're told that the wait time at a bus stop is a uniform distribution. Okay, so the question that brings to mind is what exactly does that mean? Okay, basically if we say that the wait time at a bus stop is a uniform distribution, it means that the probability of me waiting 30 minutes is equal to the probability of me waiting 1 minute. Okay, So say I show up at a bus stop, I've not checked the bus schedules. I want to know how long will my wait time be. I'll have a probability of, and I want to know whether my probability is going to be of a bus coming 5 minutes. What would that be? Okay, if I had a uniform distribution, the probability of waiting 5 minutes would be the same as the probability of waiting 10 minutes or the probability of waiting 20 minutes. Okay, so it's very random. There's no benefit to trying to calculate specific. As long as you know what that probability is, it's the same throughout the distribution for the duration of the distribution. Okay, so let's look at this example here. Southwest Arizona State University provides bus services to students while they're on campus. A bus arrives at the North Main Street and College Drive stop every 30 minutes. Okay, so we have 30 minutes. That's the total amount of time available to us. Okay. Students arrive at the bus stop at random times. Okay. And the fact that a student has arrived now does not mean that another student will arrive within. It's very random. Students arriving at a bus stop is random. It's not really predictable. Although that's not always 100% true if students leave class at a specific time. But let's just assume that students arrive at random times. There's no known pattern to the data. Okay. So we would consider this a uniform distribution if the arrival of one student has nothing to do with the arrival of any other student. Okay. Everybody arrives randomly, and the length of wait is random for each student. Okay. And the probability here in this situation is given as around 3.33%. The question that arises here is, how did that 0.33% get calculated? Okay. Charlie, had you figured this one out, maybe from your calculations?
No, I haven't yet.
No. Okay. All right. So the sum of all probabilities in any distribution has to add up to 1. Okay.
Okay.
And in this situation here, we're given that the length of wait is anywhere from 0 minutes if you arrive at the station and the bus arrives at that same time, to a maximum of 30 minutes wait if you arrive just after the bus left. Okay. Mm-hmm. So that's our range from 0 to 30 minutes. Okay. But we're told that the probability of any one amount of length of wait is equals to any other probability of length of wait. And the sum of all those times that you're going to calculate should equal 1. Okay. So if I was to divide this into very small units of time here, draw sublines here. Very tiny, minuscule units of time, in digits of 1, and so on and so forth, all the way to the end. And try and calculate what's the gap between those different points of time. The only way I could do that is to have a realization that the total amount of time we have is 30, but probability is based off of this number 1. Okay. So if I was to divide 1 by the total amount of time available to us, 1 divided by 30, I'd get this probability, which becomes the probability of the uniform distribution. Okay. 1 divided by 30 equals to approximately 3.33%, or 0.03333.
Mm-hmm.
Okay. So now, what type of questions can we get when we are looking at a uniform distribution? Let's go into a question. So say we get a situation where we ask, what's the probability that a student will wait for more than 25 minutes? Okay. And if that's the case here, a student waiting more than 25 minutes, we know that the bus arrives every 30 minutes. So the student's only going to wait for around at most 5 minutes, right? Okay, and if that's the case there, when we're calculating our wait time is a function because we have a uniform distribution. Our wait time is the area associated with that time space right there. So we have a total of 5 minutes right here. That's the amount of time we have available to us. And we know that the height of our uniform distribution was 0.0333. Okay. So to calculate what's the probability, we simply do our calculation of the height multiplied by its base. And we get an amount of 16.67%. Okay, so anytime you have a uniform distribution example and you're told how much time or how much distance is there between one point and another, the catch is the question that you're going to have is how high is this distribution? I need to know how high this, what this height is going to be. And that height is always going to be 1 divided by the range that you have on the base here. Okay.
So multiply that times the amount of, in this case, 5 minutes?
Yes.
Okay.
Okay. So there are many different ways that a scenario might be posed to you here. It could be what's the probability that a student will wait between 10 and 20 minutes? It's pretty much the same as asking the same question that's been posed here. All you have to do is know what's the range between 10 and 20. That's a gap of 10 minutes multiplied by the height of the distribution. And that'll give you the probability that the student is going to wait 10 minutes. So if I got that question and the question was, what's the probability that I'm going to wait, that a student is going to wait between 10 and 20 minutes, I'll get the range. So I'll do a 20 minus 10, which would equals 10. Okay. And to that, I'll multiply, oh my goodness. I'll multiply that by the height of the distribution, which is 0.033. And that will give me the probability of what? That's 10. So we're going to have 0.33. Okay. So that tells me that there is a 33% chance that somebody will wait between 10 and 20 minutes for the bus.
Why is
Could you repeat that?
15 in there on this chart? Just because they roll.
That's just your mean, the mean amount of time, the difference between the lowest point and the highest point. Okay. If you ask what's the mean,
I know why it was on this example.
What's that?
I just didn't know why it was in this example. They didn't seem to refer to it at all.
Oh, yeah. 15 is the mean of the distribution. Okay. The mean of the distribution is simply, for a uniform distribution, it's simply that midpoint. So if you ever ask what's the mean or the median of a uniform distribution, you just ask what's that midpoint. Okay. All right. So, oh yeah, there you go. So uniform distributions are interesting, but they are not used as much as the normal distribution. So this is the one that you should, if you're to take anything away from a discussion of probability distributions, the normal distribution is what we most often use in business. Okay, but there are a whole bunch of other distributions that are also discussed, and they each have specific instances where they're used. Okay, so the normal distribution is the most common, most easily recognizable type of distribution. And a good example would be if we're to go to any department in an organization and say, what's the average weight of employees within this department? Okay, a normal distribution should actually be able to map that pretty well. Okay, so it's bell-shaped with one peak. It's symmetric in nature, and then it has this quality where the ends of the bell never touch the base. Okay, that's called it's asymptotic. Okay, so pretty much looks like this. Very simple, and for any range of data that you'd get that's bell shape, that has a normal distribution, you'd always have something that looks like this. It might be slightly taller, it might be slightly flatter, and the height of it explains how much variation you have. Okay, so if you have, I think I have, the book has some drawings on that. Yeah, right here. Okay, so in your textbook, you have these three diagrams. And let's look at the first one here and try and understand it better. Okay. So let's go back to an example of weights within a department. In the first example, there's a blue line here which has the lowest peak. Okay. That is different from is that red or orange? That has the highest peak. And the difference, if I was to explain it in layman's terms, is that if these are two different offices, and we're looking at the weights for people within the offices, the office that is characterized by this red line here has people whose weights are pretty close to each other. Okay, everyone has, the variation is very minimal. Okay, the one in blue here has people who have the exact same mean. The mean weight is exactly the same as for the other office, but there's a much greater spread. There might be some people who are much more obese, a whole bunch of people who are really skinny. So the variation is much wider, and that's explains the lowest slope and the widest spread. Uh-oh, my internet connection is unstable. If you look at the second chart here, we have a situation where, again, let's consider offices and weights, and I know that's different.
Yeah, you keep bugging out on me.
What's that? Can you hear me okay, or is the signal?
You keep going in and out.
Oh.
You go away.
I'm wondering whether I should log in. Okay, let me just continue. Just let me know if you can't hear me. Okay. So we could also have a situation where
I will.
Can you hear me? No.
You went out just a little bit, but you're fine. Seems like when you touch your mouse, I don't know, got a loose wire or something.
Oh, okay. So whenever you see any of these types of distributions, just automatically know that this might be related to a normal distribution. Okay, as long as it has that bell-shaped curve, that's something that we'd be interested in.
All right.
Okay. Now, it's good to know about the normal distribution, but something that might make our lives easier than a normal distribution is a standard normal probability distribution. And basically, this takes whatever it is that we're looking at and standardizes it. And meaning, basically, that we center everything around 3 points. Okay. We're gonna, instead of looking at if this was, let's look at this first diagram here. If this was the mean was 19.4, say 20, yeah, it's written here, 20 years of service. We'll take that information and standardize it by changing this 20 years to be equal to 0. Okay. And there's a reason for doing that, is that it enables us to even compare different samples in a much easier way. Okay. So how do you go about standardizing information? You take the information you have and you translate it into what's considered a z-score. Okay. And the z-score is calculated by, you need to calculate certain aspects of your data. You need to know what your mean is for your distribution. You need to know what's your standard deviation for the distribution. Okay, so you have to calculate your mean, you have to calculate your standard deviation to be able to calculate your z-score. Okay, the z-score is just another function. You have a question?
No.
Okay.
I'm good.
All right. So the z-score is basically, it gives you a measure of the distance between any values within your population. If you're looking at the weights, say there's somebody called Bill who weighs a certain amount. So if let me type this here and let's make it more practical. So say Bill weighs 220 pounds. Okay, that is my X right here. And let's say that the average weight of the people in the office is 180. Okay, that's mu right there.
Yeah.
And the standard deviation is basically a calculation that should show you how much variation exists within the population. And that's something that you'd have to calculate or you'd be given in most questions. And that could be anything. Let's just assume a simple number of 10. Okay. So if I did the math here,
Will most give us the standard deviation?
What's that?
Will most questions give us the standard deviation?
Yes, most questions will give the standard deviation.
Calculate it most times.
Yeah. No, most of the questions would give it to you.
Okay.
But if you have to calculate it, it's actually not too hard. You have two options. You can either use Excel's standard deviation function or calculate it manually. But most questions will actually give you the standard deviation. Okay. So it's just basically a measure of how far on average people are from that mean. Okay. So this number of 10 here tells me that on average, the average weight is approximately 10, either plus 10 or minus 10 of 180, plus or minus 180, should I say, 10 pounds plus or minus 180. Okay, so if you do the maths in this situation here, what do we get? We get 4, 220, that gives us a 4. Okay, so what does that 4 tell me? That 4 tells me that this person, whose name is Bill, his weight is 4 standard deviations away from the mean. Okay. In other words, Bill is an outlier. His weight for that department is higher than the average. Anything above 3 standard deviations puts you as an outlier. Okay. So converting it from just a regular normal distribution to a standard normal distribution makes it easier for you to both visualize and explain your data slightly more clearly. Okay. So it begs the question, what's the standard deviation away? 1 standard deviation, 2 standard deviations, 3 standard deviation, what does that actually mean? Okay, so clear this.
That goes back to that empirical thing we talked about last week.
Which is also included here. Okay. But for the z-table, once you've figured out that number for your z-score, you've done the math here, calculated that z-score, you have to then go and look up to interpret it from the z-table. Okay. So for example, if you have a z-score of 1.5, that should tell you something about what percentage of people have a weight below your weight, if we're looking at weights, okay? So if my z-score is 1.5, then I would say that on average, I weigh more than 43.32 plus 50%, because there's this whole lower section of the distribution. So we have our mean here was 283. Below the mean, we have a whole bunch of people whose weight are less than the mean. And above the mean is anything to the right-hand side of this. Should use a different example. Anyway, I'll continue with my example of weights just for clarity purposes here, okay? But basically, if I calculate a z-score of 1.5, what that tells me is that my weight is approximately 50% plus 43.32%, which equals to 93.33. So I'm pretty much heavier than almost everybody within that department, if that was a weight. Okay. That's what the z-score tells me. So a standardized, this is how a standardized normal distribution makes it easier to understand what the normal curve is about than just looking at the normal curve.
Right. So the z-score, if it's 1, will be equal to the mean, or is 0 equal to the mean?
0 is equal to the mean.
Okay.
0 means that there's no deviation. So if here we're told the mean is 283, right? A z-score of 0 tells me that I picked up a person whose weight was exactly 283.
Okay.
Okay. A z-score of 1 tells me that I would find myself, I don't know, somewhere maybe around here. And that could be like maybe 284 something, or whatever it is that 1 equals. But once I got that 1, I have to go back into a z-table. Let me pull up a z-table online. Yep. Z-table. Nope, I didn't want ztable.com. Anyway, let's use ztable.com. Any of this is good. You should have a z-table at the back of your textbook. Deny. So you asked for a z-score of 1. If you do the math, would fall right here, okay? So 1.00 would be 80.8413, okay? Which means that 84% of all the data points will be less than that specific data point.
Okay.
Okay. And that's 1 standard deviation above the mean. You can have a z-score of -1, which would be -1 is 0.1587, which tells me that 15%, almost 16% of the entire sample population is less than that specific observation. Okay. That's
number.
What's that?
Is the -1 number and the 1 number, if you add them together, always come up to a whole number?
Nope.
Okay.
You wouldn't want to add them together.
No, I'm just saying that it looked like you have got 0.1587 here, and if you go down, scroll down to your 1.
Okay. Here.
Yeah.
Okay.
0.8413. If you add those 2 numbers together, do you not get 1?
Oh, yes, you do. You do.
And is that true on the negative and the positive side of it? Which, if it's an equal bell curve, it should be.
Yes, it should be. Okay, so basically, let's look at this here. Okay, so this is, let's assume that this z-score right here, this is equals to 1. Okay, and your -1 would be somewhere exactly the same, someplace exactly the same on the opposite side, right?
Okay.
So it would be maybe somewhere right here.
Yeah. Okay.
Now, if you look at the if this is -1, then what you get from the table is this area right here. Okay. And +1, which would be here, is now everything all the way down there. Okay. And the reason why it adds up to 1, your -1 plus 1, is because this area down here is the same as the area that's left over right on the top here. Okay.
Okay.
But whenever you look at your z-score, it's always the data to the left of the number you're looking at.
Okay.
Okay. So your z-score is always to the left. So any number that you're looking at in this table here is the data to the left of the score. Okay. Another example would be if you look at this, says a z-score of 0.7 being 0.75. That tells me that if I had my z-score of 0.7 right here, the data to the left of it will be 75% of all the data points. Okay. Hope that makes sense.
Really?
Not really. Okay, let's look at it again.
Just
ask a question.
I'll figure it out.
Oh, okay. So just remember, your z-score is basically going to tell you what percentage of all the data points lie to the left of that specific z. Okay. So let's go back to. Let's clear all the drawings. So that's basically how you'd read a z-table. Whenever you have like a 1.5, you're reading everything from this line right here and to your left. Okay, so this is an example that we could have here where we have like a taxi system, and we're told that the average, what is this? This is how much they make. Hold on. The average wage of an Uber driver. Okay, and we're told that the average is they have a mean of $1,000 a week and a standard deviation of $100. Okay, so the average amount that the drivers make is 1,000, and this can vary anywhere from 900 to 1,000 to 1,100. Okay, that's basically what that standard deviation. That's one standard deviation from the mean. Okay. And the first question here is, what's the Z value of income for a driver who earns $1,100? Okay. So in that case there, you take that individual observation, which was 1,100, subtract the mean from that, and divide it by your standard deviation, and you get a Z-score of 1. Okay. So that Z-score of 1, when you now take that number and take it to the table, look up what does 1 equate to on the table. Okay, and then that then tells you on average how much does this driver make compared to other drivers. Okay, the next question is, what's this value of income for a driver who earns $900? In this case, that's -1. Okay, so on your table here again, you're looking at 1 versus -1 and getting the data for those 2 points. Okay, so the empirical rule, I think, did you speak about this last week? I think we did.
Yeah, we did.
It says that if you have a distribution that follows a normal distribution, approximately 68% of your data will fall within 1 standard deviation from the mean. Approximately 95% of your data will fall within 2 standard deviations, and almost everything, or 99.7% of your data will be included in 3 standard deviations from the mean. Okay, so anything beyond 3 standard deviations is usually considered an outlier. Okay, when you're doing those box plots or outliers, those usually would be found somewhere way out here or way out here somewhere. Okay, but most of your observations would be found within this bell curve. Okay, that's basically what the empirical rule talks about. I don't know whether there were any questions on this. I'm almost, I think I have 4 more minutes and then this system is gonna kick me out.
Yeah, all right.
You guys are okay? Okay.
I'm good.
A question that you could get is something similar to this, where you ask, what's the percentage of drivers who earn between between $9.50 and $10.50 a week? Okay, and if that's the case, then we're looking at, if this is, for example, $9.50 and $10.50 a week, and let me go back to, so assume that is 9. Oh my goodness, I really need to buy a computer pen. So that is $9.50, and here we have our $10.50, and we asked to calculate the areas associated with that gap between those two different earnings. Okay, how would you guys go about doing this?
I don't know.
Okay, so it will be a two-step process where you first of all calculate the z-score for this upper limit, and then calculate the z-score for this lower one. Go into the z-score tables, get the values associated with both and subtract them. Okay, so let's start with the $10.50. Our z-score for the $10.50 would be that z would equal $10.50. Oh my goodness. Let's do this in Excel. So the z-score for the upper limit would equal $10.50 minus the mean. And what was our mean? 1,000. And from that, I'll divide that by our standard deviation, which was 100. And I'll get a z-score of 0.5. I'll do the same with the lower quantity, which was 950, and I get a negative 0.5. Okay, so this is that's one z-score, and that's a second z-score. Now I go to the z-tables and try and get the numbers associated with that. So 0.5 is 6915. 0.6915. Nope, 0.6915. And the lower limit was negative 0.5, which is 0.385. Okay. Or if you prefer to see these as decimal points, which is perfectly fine. I have 69 for the upper limit, 69% and 31% for the lower limit. Okay, so the question was, what was that area between the two? Oops, something disappeared here. So I'll just get the difference between that 69% and the 31%. And that then becomes the answer to my question. Okay, so this 38 is the area. 38% of the data points are going to fall within that region from 950 to 1050. Okay.
Mm-hmm.
So it's just a matter of, take one, subtract it from, take the z percentile, subtract it from the second z percentile, and you have your answer.
Okay.
Okay. All right. I'm going to maybe call it a night. Might have to have a second Zoom session maybe on the weekend. But hopefully, do you have any questions before I end the session?
I don't have any questions right now. I need to go back and do the problems and the homework. And then if I have some, if it's okay, I'll just email you those questions.
All right. Okay. So yeah, and I'll see if we can make time on the weekend to finish up this. It shouldn't take more than 30 minutes for what's remaining.
Okay. I don't know whether I can do it over the weekend, but
yeah, it's fine. If you can't, you can always just because I'm going to record and post this to YouTube, so you'll be able to access it anyway.
All right. Perfect.
All right.
Thank you.
All right. You all have a good evening.
You do the same. I appreciate your effort.
Oh, anytime. Thanks. Okay.